Limits at infinity and horizontal asymptotes. Our objective in this lesson is to be able to determine limits at infinity, find horizontal asymptotes of a function, and make connections between the limits at infinity and horizontal asymptotes. A limit at infinity means that the limit of a function as x approaches plus or minus infinity equals a value, and that value that the limit equals gives us the horizontal asymptote, the equation y equals L. Verbally, what that means is the function is approaching a value as x increases or decreases without bound. Notice how similar that is to the infinite limits. In the infinite limits, x was approaching a value while the function was increasing or decreasing without bound. This time, x is increasing or decreasing without bound as the function approaches a value. Now, analytically, one of the easiest ways to determine the limit at infinity and the horizontal asymptote is to compare the rate of growth in the numerator versus the denominator. We should also consider the behavior of the functions separately from each other. Now, here are some examples of ways that we can look at what that means to compare the rate of growth. Now, this is terminology that I use. It's not necessarily textbook definitions. It's just a fun way to remember it. You've got bottom heavy, which is where the rate of growth in the denominator is greater than the rate of growth in the numerator. So now here's what I mean by considering the behavior of the functions separately. If you think of the graph of y equals 5, what does that look like? It's constant. It just goes left and right, and that's it. It stays at 5. Whereas the denominator, y equals x, if we think of what that graph looks like, it is a graph that is growing. So as x approaches infinity, or rather as x increases without bound, so as we look towards x getting larger, what is happening to the graph of this function versus as x getting larger here, what's happening to the graph of this function? Well, in this one, it's just staying at a steady pace, not going up. This one, looking to the right, it continues to increase without bound. Therefore, I call this bottom heavy. The denominator is growing faster than the numerator. And when the denominator grows faster, well, think of how this fraction behaves as a whole. So you have 5 over, now this is just for example, 1. And then I'm going to make the denominator bigger while the numerator stays the same, 5 over 10. And then 5 over 100. And then 5 over 1,000. And then 5 over 1,000,000, and so on and so forth. Well, what's happening to these numbers? This makes 5, this makes 1/2, this makes 1/20th. It keeps getting smaller and smaller and smaller. These values are approaching 0. So the limit of a function that is bottom heavy is going to be 0. The function is going to approach 0. So rewriting this limit, the limit as x approaches infinity of 5 over x equals 0 because this is quote-unquote bottom heavy. Let's take a look at another example that's not necessarily as obvious. Think about the graph of sine of x. What is it doing? Is it increasing? Is it decreasing as x gets bigger and bigger? It's not really increasing or decreasing at all. It's basically staying constant like y equals 5. Sine of x is just up, down, up, down. It doesn't grow or get smaller. Whereas x, like we showed here, does continue to grow. Therefore, this is another example of what it could look like to be quote-unquote bottom heavy, and therefore this limit also equals 0. Let's take a look at what I mean by top heavy. So this time, notice I just flipped these two over. So now the numerator is growing faster than the denominator. So if the numerator is growing faster, that means the function is increasing without bound, while the denominator is not doing anything. So just flip these over, and what does that make you think of? Well, 1 over 5, 10 over 5, 100 over 5, 1,000 over 5, and so on and so forth. These values are getting larger. So noticing that x is growing without bound, then this function will grow without bound. So this limit is infinity. Similarly, sine of x is a constant function. It just goes up, down, up, down, up, down. It doesn't increase or decrease, really. It just keeps going up and down, whereas the numerator is always increasing. This is another example that'll give us infinity. So with this, the limit for the quote-unquote top heavy is going to be infinity. Although, take a look at this one. Notice it's very similar to this. The only thing that I changed was, instead of x approaching positive infinity or increasing without bound, x is approaching negative infinity or decreasing without bound. Well, what does y equals x do as x gets smaller and smaller? This is what it does on this side. As x goes to the left, the function goes down. So this time, the limit is negative infinity. It's important to look at where x is headed to answer these limits. So let's revise this a little bit. When a function is top heavy, the limit will be either positive or negative infinity. So the function will be either increasing or decreasing without bound. What about when they're growing at the same rates? What I like to call equal heavy. Take a look at these very simplified examples. So this, the rate of growth, and this one, the rate of growth, are the same. They're both using the function y equals x, so they're both growing at the same rate. Now, because this function is very simplified, I can easily just cancel this out, and you can see what we get. 5 over 2. But ultimately, that's the shortcut to figuring out these limits at infinity, is we're taking the leading coefficients. So the function will be approaching, I'm going to call it a over b, where a and b are the leading coefficients. Notice in the next example, it looks a little bit different. It's almost deceiving, and it looks like the denominator will be growing at a faster rate because of this degree being larger. X squared is a larger polynomial than y equals x. This function will be growing at a faster rate because the degree is higher. However, if we notice that there's a radical, that changes what we see under the radical. Think about it this way. The square root of x squared. What is that? Well, technically, because when I square a number, it becomes positive, I don't know what that x could have been. So I have to think about it being positive or negative x. It's like this. As x is approaching positive infinity, then the square root of x squared will be positive x because the x values are getting larger. But as x approaches negative infinity, the square root of x squared is going to be negative x because the x values are getting smaller. They're getting more negative. So we've got to be careful that we notice, where is x headed? Where is x headed? So ultimately, we see these, the square root of x squared and x, and we see they're growing at the same rate. So therefore, we're going to use the leading coefficients. 5 is the leading coefficient of the numerator. Square root of 4 is the leading coefficient of the denominator. And 5 divided by the square root of 4 can be written as 5 over 2. Similarly, leading coefficients because of the equal rate and growth, 5 in the numerator, square root of 4 in the denominator. However, because this one's going to negative and infinity, we're going to switch this sign right here. So negative 5 over 2. Now it's important to remember the connection between the limits at infinity and the horizontal asymptotes. What they mean, the limits at infinity, is that you have a horizontal asymptote in the graph because the function is approaching a value. So if we were to graph a function that had a horizontal asymptote, we would show the horizontal asymptote with a dashed line. And then it's possible that the graph could be doing anything as it approaches that horizontal asymptote to the right or to the left. Keep in mind that graphs can also have two horizontal asymptotes, and horizontal asymptotes can be crossed. So the function could be doing all sorts of crazy stuff in the middle. It's not about what's happening in the middle, it's about what's happening as x gets infinitely large or as x gets infinitely small. The function is approaching a value. Now, if we know the limit at infinity is 0, that's going to mean that the horizontal asymptote is y equals 0 because the function is approaching 0 as x gets increasingly large. Similarly, if the function is approaching infinity or increasing without bound, there's going to be no horizontal asymptote. And if this is the limit as x increases or decreases without bound, then the horizontal asymptote is the equation y equals a over b. So keep in mind that connection is extremely important. Let's take a look at some more examples. In 1 through 4, we're going to find the limit and the horizontal asymptotes, if any, of the function. So I see that it's a limit at infinity. X is growing increasingly large. So I'm going to look at the rates of growth. If they are just two polynomials, it's easy to see, well, this has a larger degree, therefore this one is bottom heavy, which again is just my shortcut way to remember it. Therefore, this limit equals 0. So I found the limit, and now I can write the horizontal asymptote. It's the equation y equals 0, and it must be an equation because it's a line. This one, which comes from an AP problem, again, I see polynomial over polynomial. At first glance, it looks like it's top-heavy because that's as n squared and that's as n. But sometimes the functions aren't written in standard form. So let's look closely. And looking closely, I see n squared and n squared. These functions are growing at the same rate. So now I use the leading coefficients. In the numerator, 4 is the leading coefficient. In the denominator, 1. Positive 1 is the leading coefficient. So this limit is the ratio of the coefficients, 4 over 1. Now I do also have to notice that n is increasing without bound so that I'm not switching the signs here. 4 over 1 is fine, or I can say 4. Now I can write my horizontal asymptote, y equals 4. Number 3, we're going to do in two parts. Notice y. I've got the limit as x approaches positive infinity and as x approaches negative infinity of the same function. So let's observe what these two functions do. Y equals 5x, if we graph it, is a linear function that looks like this. Y equals e to the x is an exponential function that when we graph it, looks like this. Notice that to the right, how these functions grow. This one is growing faster. So as x gets large, infinitely large, looking at it to the right, this is towards the positive infinity for x values, then this function is going to be bottom heavy. And what happens to the limit when it's bottom heavy, growing faster on the bottom? The limit is 0. So there is a horizontal asymptote, y equals 0. How about the other side? As x goes to negative infinity, well, observe what's happening to the graphs on the left. On the negative side, this graph is going down, and this graph on the negative side is headed towards 0. So this one is growing and growing and growing negatively, while this one is getting smaller and smaller and smaller. So this one is growing faster. This graph is top heavy. Because it's top heavy, the limit is going to be either positive or negative infinity. But because the left side is going down, or I shouldn't say but, I should say and, because the left side is going down, this will be negative infinity. When the limit is positive or negative infinity, there is no horizontal asymptote. Well, at least not towards the left. We know that the function will be approaching a value as the x values increase without bound. So while there is a horizontal asymptote, the left side of the function does not approach that horizontal asymptote. Let's make a note about that. The left side of the function doesn't, or let's say does not, as emphasis, approach the horizontal asymptote. Now I'm going to give you a quick sketch of what this graph looks like because I graphed it. There is a horizontal asymptote, like we said, y equals 0, so we can sketch that. To the right, what the function will do is approach the asymptote. To the left, the function will decrease without bound. So it's going to look something like that. Let's take a look at one more of these. What is the limit as x approaches positive infinity for this rational function? So again, notice I've got two scenarios here. X approaches positive infinity, x approaches negative infinity. Let's examine the rates of growth. Because this is x and this is square root of x squared, we're going to say that these are growing equal heavy. Therefore, I'm going to take the leading coefficients. 3 is in front of the x, square root of 2 is in front of the x squared, so this limit is 3 over square root of 2. If x is decreasing without bound, same function, notice, but x is decreasing without bound, then this is negative 3 over square root of 2. Now, because there are two different limits as x increases or decreases without bound, there are going to be two horizontal asymptotes. Y equals 3 over square root of 2 and y equals negative 3 over square root of 2. Number 5 from an AP exam. We really need to understand the connection between limits at infinity and horizontal asymptotes. Let's read the question. For x greater than or equal to 0, the horizontal line y equals 2 is an asymptote for the graph of the function f. Which of the following statements must be true? So think about this. Horizontal line y equals 2 is an asymptote. So just a quick sketch. Now we know that a horizontal asymptote means that the function will be approaching a value. In this case, the value is 2. So the function is approaching 2. Now, is it going to approach 2 as x gets infinitely large, or as x gets infinitely small, or both? The function could be going like this to the right. It could be going like this to the left. If there's a horizontal line that is an asymptote, one of those things has to happen. So which of these following statements must be true? F of 0 equals 2. Is it true that f of 0, at 0, the x value has to equal 2? It could, but does it have to? No, it doesn't. Is it true that the y values can't equal 2 for all x greater than 0? Sorry, greater than or equal to 0. So that's saying the y values can't hit 2. So the function can't do this? No, it could. So that doesn't have to be true. Is it true that f of 2 is undefined? That means that at the x value 2, there is no function value. Well, if I draw the graph like this, there's a function value, so that's not a must either. Is it true that the limit as x approaches 2 equals infinity? Well, when x approaches a number and the limit is infinity, that gives us a vertical asymptote. And that's not what we're given here, so that's not true. Finally, the limit as x approaches infinity, notice that's a limit at infinity, for the function equals 2. And because the function is approaching 2, this is true. This is the connection we need to make to horizontal asymptotes. This must be true. Thanks for watching.